Hello everyone, welcome back to our channel here. We're going to talk about quadratic functions and equations, and specifically how it relates to Math 20-1 and all the things we can do with it. So this playlist will have about, I think it's 9 lessons in total about quadratics, and we'll start with the first one here that we'll deal again with all about factoring. And you saw factoring for the first time, well, with polynomials in Math 10C, and how to take them apart, and a couple different techniques that we could use to do that. So we need a quick review on factoring, and that'll be this first lesson, and then we get into really all of the things we can do with a quadratic equation. So if you've got something that's your basic trinomial where a is 1, and remember that your basic trinomial looks something like ax squared plus bx plus c. So when it talks about a being 1, it's your coefficient of your squared term. And the way that we could use all of our other techniques to factor this again was basically looking for two numbers that follow two simple conditions. And they always tried to multiply to your constant number and add together to your number in the middle. So if you think about two numbers that would multiply to negative 21, but the same two numbers add to minus 4, the numbers that would do that are some combination of 7 and 3, but the signs need to work out also, and in order to add to a negative, my larger of the two should be a negative number. So I've got my two numbers I can use here to make up my factors, and essentially that minus 7 and that plus 3 is what we split our middle term into. So if you think about undoing the collecting like term step for a polynomial, really we're just taking that negative 4x and representing it as negative 7x's and positive 3x's. So really, those two pieces are going to be, our two factors. And factors are things that you can multiply together to get your original expression. The same thing was true with numbers. So two factors of 21 are 7 and 3. Multiply them together to get 21. The same thing is true for polynomials. And you can do this even if the coefficient isn't 1 in front of it. There may just be something called a GCF in there as well. So think about that as being the greatest common factor, right? There's something that all three of these terms have in common, and they're all multiples of 2. So your greatest common factor is 2, which will leave you with a squared minus a minus 12. And I go into a lot more depth with factoring in some of the Math 10 videos. So if you do want more in-depth factoring techniques and resources, like me explaining it a lot further than I'm going to here, you can check those out. It's just like with 20-1, you have to be able to factor super quickly very often for quadratics and even rational expressions as well. So if factoring is a problem for you, it might be worth your time to spend the time watching the Math 10 video, where I go way more in depth in this. Like a really, this video will probably end up being, I'm gonna guess, around half an hour with all the things, and that's like me speeding through the factoring, because a lot of the things that we're gonna do for quadratics, things are gonna need to be factored very quickly in order to use them to their full potential, to do all the things we have to do. So if I factor this one, again, finding those two numbers to satisfy those two conditions, multiply to negative 12, add to negative 1, you're going to see it's a minus 4 and a plus 3. So I've got it factored, and this represents the same thing as our polynomial in the beginning. One of the other techniques we talked about was in Math 10 was a difference of squares, which said that if your first term was a perfect square, your second term also a perfect square, as long as you have a subtraction in the middle, a difference, you can follow this shortcut pattern where you take the square root of the first term, so the square root of m squared is m, the square root of 16n squared is 4n, and you place different signs in between them. And the reason why the signs have to be different, if you were to expand this using some distributive property techniques and multiplication of binomials, your middle term will end up canceling out, right? I'm going to have negative 4nm's plus 4nm's. They will disappear for 0. So the signs need to be different. If they're both negatives, the middle term won't cancel. If they're both positives, the middle term won't cancel again. Now the other one we talked about is, well, what happens if there's no common factor and there's no possible way to simplify things any further? This was the last resort type of method, where I can use something called decomposition. So we'll find two numbers that satisfy two conditions again, but this time we're going to take the number in front of our squared term and our last number, the constant, and that's what we're going to multiply together, right? So we want to find two numbers that multiply to a positive 36, but the same two numbers will add to a positive 12. Okay, and the two numbers to make that possible are 6 and 6. Right? 6 times 6 is 36, add them together for 12. And the reason why we call it decomposition, we're really splitting up that middle term, decomposing it into two parts. So we've got 9b squared plus 6b's plus 6 more b's plus 4. Really, we're undoing that collecting of like terms, right? Splitting them back up into their two parts. Once we did that, we could group things together, right? So the first two terms go together, the last two terms also go together, and then in each of those groups of two, you can see what they have in common. So the first one will have a 3b in common to leave us with a 3b plus 2, and the second one has a 2 in common, again, to leave you with a 3b plus 2, and the goal here is to make those brackets the same, right? If they're different at this step, something went wrong. So once I got to there, well, my brackets again are going to act like a common factor, right? The two big terms are 3b times 3b plus 2, right? That's one of my terms. My other term is on the other side of that addition sign. So in red is what they have in common. The 3b plus 2 was our greatest common factor of those brackets. So your two factors are going to be, well, one of them's 3b plus 2. The other one happens to be the same thing because the numbers we used to do this were exactly the same value. So I know my factors are going to be the same also, which you may also see this be written as 3b plus 2 squared. Okay, so you'll have that in there as well, which either one means the same thing. It doesn't really make a difference. And that leads us into talking about a perfect square trinomial, because well, if I just read this, in a perfect square trinomial, the first and last terms must be perfect squares. The middle term must be twice the product of the square roots of the first and last terms. That's what we're going to look for. So if we test this out for the one that you see there, well, if I take the first term and square root it, I get x. If I take the last term, which is 25, and you also square root that, you get 5. And it does say the middle term must be twice the product of the square roots. I found the square root, so here's the test for that middle term. Well, I get 5 multiplied with x for 5x, but it has to be twice that, so multiply it by 2. I've got my middle term for 10x, so I know this is a perfect square polynomial. And in order to factor it, well, you can take your square root of the first one, which is x. That goes into the beginning part of your bracket. Square root of the last term, which is 5, that goes in also. But the sign you're going to place, if it's a perfect square, the signs have to be the same. And it's always going to come from the sign in between your squared term and your regular just, power of 1 term. So this one, they're both going to be x plus 5s, which is really like saying x plus 5 squared. So our last trinomial was a perfect square one as well. So if you want to try factoring it using the shortcuts, you can, and all the links will be provided to you in the description box. You'll have everything filled in. So you can try out that technique if you want. One of the things you're usually asked to do is determine if something is a factor of a polynomial. Or when we get into things like zeros and x-intercepts, it has more of an actual meaning and a purpose. But if I can't factor it, then I can't do any of those things. So there's a couple here. I won't do each of them in the video. Like, I'll do one of them so you can have an example, and then you can see the answer key in one of those links that you'll have there. So we'll talk about the first one. We're looking for x plus 3 as a factor of this polynomial. So one of the things we're always going to check for first, to make the numbers a little smaller, look to see if there is a greatest common factor. Now I know that the coefficients of 4, 10, and negative 6 are all even, so I know that 2 is a common factor to them. So let's cut everything in half. Makes the numbers a little easier to work with. So now we're going to look for two numbers that satisfy those two conditions again. We want to multiply to a negative 6, but add to a 5. So I know that some combination of 6 and 1 will do it. And if I want to add to a positive, that means my 1's negative. So I've got my two numbers. Now we can do our decomposition. So 2x squared. It doesn't really matter where you place your numbers, so I'll put the negative one first, positive one second. Makes no difference which one goes where. But now that I've got them in there, well, let's make some groups. So there's the first one. We'll put those together. Plus sign stays. 6x minus 3 is our other group, and in those groups that we made, we'll look for some things that they might have in common. So the first group of 2 looks like they only have an x in common. So x is our common factor. We're left with 2x minus 1. Plus, the second group has a 3 in common, and again you're left with a 2x minus 1. So I know I did this right. So if I take each of my factors, I've got a 2x minus 1 and x plus 3. And we were asked to determine if x plus 3 is a factor of the following. Yes, it is. I can see it in my factored form. So yes, x plus 3 is a factor. Okay, so I've got it in there. I can see it. We're good. You can try out the one underneath to make sure it is or is not a factor. And again, I'll have the key for you. So just try and factor it using, maybe this technique for decomposition. Maybe it's a different technique that you have. Makes no difference. It'll work the same way. Okay. This question, very, very, very similar. So again, I'll leave this one. It's very much so linked to the one we just did. So try and factor them. You can determine if that is going to be a factor or not. You can check. We will do both of these ones because the fractions cause people a little bit of anxiety, especially decimals. Okay, so one of the techniques you can use here is to factor out that decimal, which is instead thinking about, like, if you make that decimal go away, each decimal place is a power of 10, right? So if I move the decimal, it's like multiplying everything by 10. And it's not like an equation where I multiply the right side and the left side of the equal sign by something, because I don't have an equal sign. So I have to still remember to account for that fact that I'm moving that decimal. Mathematically, it still has to be the same. So if I factor out 0.1, which is the same thing like multiplying by 10, I have to think about also undoing that multiply by 10. So if I make everything a power of 10 larger than it currently is, and I make it 10x squared plus 14x minus 12, well, I've changed the value of everything, right? It doesn't look the same anymore. It's not the same polynomial. So my common factor on the outside should be something to undo that change. And if I want to make this, the exact same thing as before, well, that's the same as saying, well, multiply everything by 1 over 10, which is like dividing by 10. So 1 over 10 multiplied by 10 works out to be 1. 1 over 10 multiplied by 14 is 1.4. Same thing for the 12 gets you your 1.2. So mathematically, I've changed nothing now that my coefficient is there. And I have to keep it the entire time. And now we can go factor this like normal. So I've got a coefficient 1 over 10. Each of the terms inside the set of brackets are even, which means 2 is a common factor to them. So we'll cut everything in half now. And I can combine my coefficients now. If I've got 1 over 10 multiplied by 2, that's the same thing as saying but 2 over 10, which is the same thing as saying 1 over 5. That's where I was going with this. So 2 over 10 is the same thing as 1/5, and now I can go factor this like normal. So look for two numbers again that satisfy those conditions for us. So you want to this time multiply to negative 30, add to positive 7. So 10 and negative 3 will do it. So let's split this up. So we're going to have a positive 10x, a minus 3x, and there's our minus 6. If you make your groups like we've done before, this time it's got a negative sign to worry about. So there's my 5x squared plus 10x. There's a minus sign this time, so the other two terms will switch signs when we put the brackets around them. And now we can just factor. Okay, so we'll look for a common factor in the first set, so a 5x, so you've got an x plus 2 that remains inside. Take out a 3 from the other one for, again, an x plus 2. Brackets are the same, so this is good. So 1 over 5, you've got 5x minus 3 as a factor, and an x plus 2. Okay, and again, we go way more in depth in those Math 10 videos on factoring, so if you're still feeling a bit uneasy about that, I would strongly advise you to go find that video. There's a bunch of them on common factoring techniques, decomposition, difference of squares, all of those things are in there, each with their own dedicated video. Okay, so there it is, fully factored. We can do the same thing if there are fractions as well. So if my fraction that is the problem is a divide by 2, that's what's causing us the issue. Well, I can double everything to make sure the fraction goes away. So I multiplied everything by 2, but now I changed the value of it, so I really have to account for that change by undoing it. If I put a factor of 1/2 on the outside, I've accounted for it, right? If you cut everything in half, you're right back to where you started. And so now if I go to factor this, well, I don't have a common factor this time between 629 and 28, so that's a problem. So we're going to take our number in front, and we want to multiply to get us 168, I believe, and we want to add together to our number in the middle, right? We want to add together to get this. The two numbers that are going to do it are a -8 and a -21. Right? Those are the two numbers that will multiply to 168, add to -29. Okay, so they'll combine together, so I can do my decomposition step no differently than we did before. I just have a factor of 1/2 on the outside. So 6x squared minus 21x minus 8x plus 28. Just make your groups of 2 once more, and you can see that every question really is the same, and we use the same techniques all the time. So the better you are at them, the more proficient you get at factoring, the easier this unit becomes. So let's say go to 3x there. So that's 2x minus 7. Take out a 4 from the other one, and again you've got a 2x minus 7. So I've got my brackets the same again, so this is good. So fully factored form, 1/2 is a factor, 2x minus 7 is a factor, and 3x minus 4 is your last one. Okay, so there you go. Okay, so factoring a question should take you no more than 30 seconds if you're in Math 20-1, because of the other complexities that get added to this. Right? Factoring is a Math 10 concept. We just build on it in Math 20. How can you check that you factored a trinomial properly? Well, what you can do, if you want to check if you factored this right, there's a couple ways. You could use your graphing calculator to graph the factored form, graph the original polynomial, and your graph that you should see should be the same. That's one way. You can try to multiply everything out and make sure you got back to the original. It's more time consuming, but it'll work. You could also just pick a number for x and plug it into this to make sure that you end up with the same thing. I would avoid picking 0, because that will cancel everything out and everything will end up being 0. But pick a number like 2, that might work. If x is 2, make sure it's the same in your original expression as your factored form. You should get the same results. That's another way. But here's where we start to make this a little bit more complicated. Now, some of the expressions are not going to be as straightforward as they used to be, and we're going to have to use something called a substitution. Now, the part that causes a problem for this, this one kind of looks like, it kind of looks like a regular polynomial of x squared plus bx plus c. It kind of looks like that generic one where I have something squared, something multiplied by a constant, and then just an actual constant. So we can use what we call a substitution. So it's really the x plus 3 that looks weird here, right? If you set that expression, that binomial, equal to just a letter, you can pick whatever letter you want. You can see underneath how what we had before, if x plus 3 is equal to a, well, this just becomes a squared minus 6a minus 16. And I can factor that pretty easily, since the coefficient of that squared term is 1. Well, now I know the two numbers that multiply to -16 and add to -6, I'll write it in here, have to be some combination of 8 and 2, where my 2 is the one that's negative. So I know my factors are going to be a plus 8 and a minus 2. The problem is our original question was in terms of x, not in terms of capital A. So if this was our substitution, our last step should be to replace it in our factored form to get what we actually should have, our question in terms of. So a is actually x plus 3, so let's put that back in. And then you can simplify and collect your constants as your last step. So x plus 11, hang on a sec. It's x plus 3. Make sure I have... Oh, that should be a minus 8. I got my signs backwards. That's why. So let me fix this. Okay, so it should be a negative 8 and a positive 2 to add to a negative. So there we go. Let's fix this one up. That's much better. Okay, so x plus 3 minus 8 and x plus 3 plus 2. So I'm going to end up with an x minus 5 and an x plus 5. And there it is, factored. I didn't have to deal with squaring things, distributive property, and collecting like terms, which you could have, right? You can multiply everything out and then factor it, but this is much, much easier. That took us all of 25 seconds, right? So much easier to remember that you can use a substitution to do this. Okay, so let's try this out here as well. Again, the problem is this 3x minus 4, right? That's what's making this look more complex. So let's let b this time be equal to 3x minus 4. The letter doesn't matter. If that's what b is, 6b squared minus 21b plus 15 is our new resulting polynomial to factor. So all the same techniques are true. Look for a common factor first. 3 is a good one. So you've got 2b squared minus 7b plus 5. Okay, you can factor that pretty easily. Find two numbers that multiply to 10 but add to negative 7, some combination of 5 and 2. Both have to be negative this time for this to work. So 3 is our common factor. 2b squared minus 5b minus 2b plus 5. Split them up again into two groups. Well, two groups of 2, I should say. Minus signs out, switch the signs inside so it's mathematically the same. Look for your common factors inside. So just a b to get 2b minus 5. The other one, already good. My brackets are the same. So my factored form then is going to be 3 on the outside. You're going to have a, oops, I don't need the double brackets anymore. 2b minus 5 and a b minus 1. So there it is factored. The problem is we need to replace b with 3x minus 4 because our original question was in terms of x. So that equals now 3x minus 4. So I've got a 2 multiplying by b, which is 3x minus 4, and then minus 5. Okay, so make sure that your order of operations works as well. I got all my brackets in the right place, okay? So then a 3x minus 4 minus 1. Okay, so now we can think about simplifying those brackets. So 6x minus 8 minus 5, 3x minus 5. Okay, so here we go, last step. 6x minus 13 and 3x minus 5. So there you go, fully factored again, replacing that substitution in the end to get things back in terms of x. There are all of the steps. Okay, and again, this is really just a factoring question right now. We haven't even started to do the quadratics things with this. So once that all comes into play, you will see how complicated this really does get. Okay. Underneath, again, there's a couple different polynomials. So I'll let you, I'll leave them blank in here if you do want to try them. And you can take a look at the answer key. They'll all be there for you. We can do all of this with the difference of squares as well, which does take us to the bottom. So we will do these three here together. Again, just talking about a difference of squares. So if you think about A here, right, there's three questions you're going to ask yourself. Maybe I'll add them to this document. Number 1, first term should be a square. Let's say first term needs to be a square. Right? It has to be a perfect square for this to work. Number 2, second term. That writing is not too pretty. Second term needs to be square. Lastly, subtraction. One of the things that students always look for is, well, yeah, I've got two squares, but there's a plus sign. Does the rule still work the same? No, it doesn't. It has to be a minus. The rule literally is difference of squares. Difference means subtract. So you need a minus sign. Okay, if there's anything else there, this doesn't work. If you have those three conditions satisfied, take your first term, square root it. Goes in first. Take your second term, square root it, it goes in second. And then you're going to get different signs in between them. Right? One is x minus y, one is x plus y. Fully factored already, nothing else to do. So a difference of squares is quite nice, provided you can recognize that you even have one. If you think about b, well, 12 is not a perfect square, neither is 3, so that's a problem. So let's take out a common factor first of 3 and see where that gets us. So now I've got 4x squared on the inside minus y squared z4. Now 4 is a perfect square, x squared is a perfect square, so the whole first term is also a perfect square, that's good. Y squared is a perfect square, z4 also a perfect square. So I know I have a difference of squares here, so I can use my shortcut. So let's get two factors going. Square root of 4x squared is 2x. Square root of y squared is y. Square root of z to the power 4 is z to the power 2. So I've got a perfect square there as well. Different signs in between. So I made the first one a minus, second one a plus. You could reverse them. It doesn't matter. The order you multiply things in makes no difference. Okay, so there it is fully factored. Now I can't do a difference of squares again because, well, now 2x is no longer a perfect square. There's no way to make it one. So I know I'm done. If you think about c, well, I've got, some binomial expression that looks like they're perfect squares, but it looks more complex. So some people will do this using a substitution. Some people will not. Either way works the same, and our end result will be no different. I'll do a substitution here because it's one of the things we talked about in this video. So let's make a equal to 2x minus 1, b equal to y plus 4. And if I use those two things as substitutions, well, now I get a squared minus b squared. That's a difference of squares by definition. If you factor it, well, you're going to have a minus b, a plus b. Replace those a's and b's with your original expression. So I know this is the format the factors will take, but I need them to be in terms of x, because that's what I started with. So 2x minus 1 minus the whole expression for b, so brackets are important there, 2x minus 1 plus y plus 4. Now I don't need the brackets for the second part here. With addition, it doesn't matter. Subtraction makes a big difference. It'll change the signs. Collect all your like terms that you can. So we've got a 2x minus y, this would be minus 5 when you collect those, and your second set of brackets will be 2x plus y plus 3 when you combine those together as well. There it is, fully factored. You could have done this without the substitution to get to this point here, but it would work out the same way as the end results. So I will leave the next couple, A, B, and C, for people to try them out if you wish, and that really brings us to the end of our section on factoring. Now, it doesn't mean factoring goes away. It will literally be here from this point on throughout 20-1. We come back to it in system of equations, we come back to irrational expressions, we come back to it in a lot of applications. There were certain questions and sequences and series that we couldn't do before, but now we can with the applications of factoring. So you'll see the next video linked up above, and all the resources will be in that description box. So hopefully we see you in the next one. Until then, take care, have a wonderful rest of your day.